Hello students, this is lecture number 11 and we are into chapter 3. Okay. So, in the last lecture video, we looked at the exact solution for 1D elasticity problem. Okay. And today we will learn about approximate solution. We will try to find one approximate solution of the problem that we solved in the last video, and the problem was we had a bar which is attached at one end and free the other end, and there is a body force B naught which is a constant. Then we had length is which is equal to L, area is A naught, and Young's modulus is E naught, and we found the exact solution which looks like U equal to U x equal to minus B naught over 2 E naught A naught x square, right, plus B naught L over E naught A naught x. Okay, and if you plot this solution, this will look like something like this. Yeah. Okay, so we are plotting ux versus x, and slope here will be 0 because there is no force at the end. Force indicates slope of u basically. So here slope is 0. So du over dx is 0, means force is 0. Here force will be maximum, du dx is maximum, and you can also see that the force here, the reaction force will be equal to summation of all the forces from here to here. So it will be the highest at this fixed end. Okay, now the question is if we want to have some approximate solution which let us say we want to approximate is something like this. Yeah, so we want to find out a solution which is like this one. So let's call this is approximate solution. Yeah. So the question is, can we find out a best linear fit for the solution? Okay, or we have like in this case this was easy, easy meaning that we have exact solution like this one. However, in different cases, when let us say you have A is changing in a complex manner, or E is also changing in a complex manner, in that case finding ux exact solution is difficult. In that case we have to assume one kind of solution. So typically this polynomial is assumed, but here I am trying to give you an example, and hence here although this quadratic equation is the exact solution, but let us say I want to find a solution, approximate solution, which is a line basically. So let us say assume we want, say we rather want an approximate solution. Okay, approximate solution, say linear okay, linear, then what to do? So, what we want is something like ux equal to alpha x plus beta. We want this, and we want the best fit. What should we do to find out what is alpha, what should be the beta, so that that represents the best fit of the solution that the original differential equation can admit. Okay. Now, we have to go back to the differential equation, and if you remember from the last lecture, the differential equation was, so not partial, so d over dx, and then we had e a du over dx plus bx equal to 0, okay, along with some boundary condition. So, boundary condition we had u 0 equal to 0, and which is essential boundary condition, and then we have E a du over dx at x equal to L is also equal to 0, and E was equal to E naught, A equal to A naught, and Bx equal to B naught. So, this was also given. Okay, and here if you assume in this case if you incorporate all those things here, so equation becomes simply E naught A naught d square u dx square plus B naught equal to 0. Here, okay, so if you see here, if we had assumed, if ux is assumed to be quadratic, right, meaning that if ux we assume as let us say a x square plus bx plus c, yeah, then okay, we are using b already here, so let us not confuse this one. So, we can write something else. So, let us write is cx plus d. Okay. If we had assumed ux like this one, then we can find out a, b, a, c and d. How? You first put this in this equation, and then we can find out what is the double derivative of u. So, what you get is 2a. So, this will be 2a e naught a naught 2a plus b naught equal to 0, and you can find out a will be equal to minus b naught over 2 e naught a naught. So, you can directly you can find out. Then you have boundary condition, you can apply x equal to 0, 0, 0 here, then you can automatically find out d equal to 0. Then you can also apply this boundary condition, and you can also find out what is the value of c. So, basically there are 3 equations here, these 3 equations. Okay, so, let me, okay. So, we have these 3 equations, yeah, and we have this a, c, d 3 unknowns, hence you can exactly find out the equations. So, it is very easy to do, yeah. So, you can find out if you assume the ux to be of quadratic form, if you assume ux equal to ax square plus cx plus d, then you can exactly find out the solution, and the solution will look like what we got earlier. Exactly we will find out. We saw that a we got as minus b naught over 2 e naught e a naught. We got this, there is no constant term here because you got d equal to 0. C you will find out equal to B naught L over E naught E naught. So, you can find out like that, because in this case exact solution happens to be a quadratic equation and hence it will fit exactly, it will fit like that. However, if we want to fit one line, if we are assuming as we wrote here, we want solution to be of this form alpha x plus beta, and whatever is the best fit we want that, then what to do? That is the question. If we are able to somehow get an approximate solution to this problem, then we can extend that to more complex problem. So, here we are seeing that if the solution, exact solution is quadratic, but you are trying to fit one linear solution. Okay. So, the problem is, if you have this differential equation and if you are assuming u to be linear, then what happens? There is no double derivative. Yeah. So, if you try to put, so our equation, differential equation is E naught A naught d square u dx square, and then you have B naught is equal to 0, and if u x equal to alpha x plus beta, then what do you get? You get d square u over dx square, you will get equal to 0. Yeah. So, if you put this here, then what happens? You get 0 plus B naught equal to 0. This kind of funny equation you get. However, you know that B naught is not equal to 0. So, it's a very strange type of situation you get, because since the equation that really tells you that this kind of solution is not admissible here simply, right. Okay. If we had some sort of equation with just single derivative, then we will then we would have been able to find or fit this solution. Okay. You can also think another way, that you have one equation here, and there are two boundary conditions typically given, right. So, you have boundary condition as you have u 0 equal to 0, and also you have E naught A naught du over dx at x equal to L equal to also 0. So, that means you have three equations, number 1, number 2 and number 3. There are three equations, and you have to satisfy, the u has to satisfy all of them, right. Then you have only two constants here, so only two unknowns and three equations. Again, it looks like there should be infinite solutions, but it's not like that. Yeah. So, there are three equations, and no, sorry, that really means that not infinite solution, the solution probably you cannot get, meaning that you have only two unknowns, you have three equations. So, too many constants basically on alpha and beta. So, finding a unique solution is difficult, it's not infinite solution. If you had more unknowns and less number of equations, that means you had infinite solution, but in this case the opposite, you have less number of unknowns alpha and beta and larger number of equations, hence you have more constraints, and finding alpha beta is much more difficult. Okay, then what to do? Okay. So, basically what we have to do is we have to find out one alternative equation. So, we have to transform this equation, okay, we call it the okay, this equation or a strong form to an approximate equation, okay, or we call it weak form. Okay. So, basically if we want to find an approximate solution, easier solution, we have to also transform this original differential equation to an easier differential equation. Easier means we also call it a weak form, okay, and the original differential equation we call it a strong form. Okay. So, from we have to transform the original strong form to a weak form, so that this can take a linear solution as well. That means we want to transform from double derivative to single derivative. Okay, that's the thing. Okay. So, hence we will have to do transformation, but how to do it? Okay. So, let us say we will write the equation again. So, let us say the equation is A naught du over dx plus b naught equal to 0. Let us say original solution, the u x is original solution, but and approximate solution, let us call V x is approximate solution, right, approximate solution. Okay. Then sorry, E naught d square dx square. Okay. So, then what happens? Then we can have, if we put this value here, then what happens? Our equations becomes E naught A naught d square V x over dx square plus b naught, which will may not be 0, as we seen earlier. For example, V x, if you have a linear fit here, then what happens? This term becomes 0. So, everything becomes 0. You have the b naught here. So, this will not be equal to 0, right. So, may not be equal to 0, right. So, we call it residual. So, we can say r x equal to residual. Okay. So, that is the error basically, residual equal to A naught A naught d square V x over dx square, okay, plus b naught. So, this is our residual. U is exact solution or a original solution, or we call original exact solution. V x is approximate solution. If you put V x in the original equation, you may not have this original differential equation becoming equal to 0, and that really means there will be some error, basically residual. So, actually this error, and then this one is the one which is residual. Okay. Now, we want to minimize the error. Yeah. So, the idea is to minimize the error, or write like this: we want an approximate solution with minimum error, right. So, this is our aim. We will find the solution, but such that the error is minimum or residual is minimum, right. Residual is 0 is the best thing, but residual will not be 0, as we know, right. If the solution here, exact solution is quadratic, if we try to fit u equal to alpha x plus beta, we know that residual will not be 0 or R x will not be 0. Then what to do? Then maybe we find out what is the residual, like let us say this is x and this is R x, okay, and residual could be something like going up and down, something like this, right. And what we want to do is somehow we integrate residual over the length 0 to L will equal to 0. We want to do something like this. So that means what happens, at some portion the error will be positive, some portion error will be negative, but if we sum it over the domain, then we will get the equal to 0. So that is one way of implementing or finding out the best fit. Or we can also do like we have a function or weight, we can also have a weight, okay, weight function, let us call it Wx, such that we have 0 to L Wx, then Rx dx equal to 0. Now weight, if you put a weight, that gives you lot of flexibility, then you can have the weight is such a way that you find out the best fit, better fit, meaning that where you know the u, there you can have a weight equal to 0, where the u is supposed to be maximum, there you can have maximum weight, so that error of u reduces, you know. So you want to have the error of u rather than error of residual, you know. So the error of u, if you want to minimize, then it is a good idea to have some kind of weightage which is also proportional to original the solution itself, so that where u is high our weight is high, where u is less our weight is less, where u is given then we take equal to 0, because we are already giving u, means our the test function or the approximate solution, whatever we give, we already apply the essential boundary condition, and since it's we already have the solution, the essential boundary condition is satisfied by the approximate solution that we are giving. So we don't want to give any weightage there, you know. So because we are already implementing, it's already satisfying the condition, so there we can have weightage equal to 0. So you will come to know more later on, okay. So here just to give you some idea basically. Another thing you can also notice here, that if we have if you see the example here, so when we have the solution as ux equal to alpha x plus beta, then we have residual or d square u dx square is equal to 0, and hence residual Rx will be equal to B naught simply. Why? Because our equation is E naught A naught d square u over dx square plus B naught is equal to 0. Yeah. Okay. So that really means that this term is equal to 0, hence your residual is simply Rx equal to B naught. So instead of having your residual as wavy, something like this one, where positive or negative cancels out, you will not have the same case here. So, what you will have in this case is residual, you have x and this is R x, and you have a constant residual something like this one, which is equal to B naught. Yeah. So, that means in this case there is no like the best fit you cannot find out, means regardless of what you take alpha and what you take beta, always your residual is equal to B naught only, and hence this kind of a strategy will not work. If you, in all the cases, your error is never going to be 0, so you always will get a error equal to B naught times L is always the error, and hence you cannot get this condition at all. Hence, if you have weight function, weighted residual, okay, so this is called weighted residual. So, if you have the weighted residual, then it may be possible. Then you may have weight function such a way that this kind of situation appears, yeah, and then it can find out the best fit in that case. Okay. So, basically let us start with this one. So, we know that weighted residuals, any function w x that comes to multiplied by residual, and if you integrate, we make it equal to 0, we will find out the best fit. Okay. So, we can write down now like here. So, this is also the previous one, this is also called the weak function or weak form, this is called the weak form. So, starting with the strong form is, we write a strong form is d over dx. So, we write now general purpose equation E A, then du over dx, right, plus b, right, this is also function of x, the E also can be function of x, A can also be a function of x, is equal to 0. This is called a strong form or the actual differential equation. Then we have weak form which is given by integral of 0 to L in this case, and we have a function or weight function w x, then d over dx E A du over dx, right, plus b x dx equal to 0. Yeah. So, we have this which will be a weak form basically, and this is true for any, okay, that is for any w x. Regardless of what w x we choose, this should be valid. Okay. So, our solution if u is the solution, even if it is a approximate solution, then regardless of what weight function we are using here, multiplying and integrating it should be equal to 0. So, hence we are writing for any w x, provided there is also this also has a boundary condition, right. And as I said earlier, at boundary condition we are not the essential boundary condition, where u is given, there we are not having any weight equal to 0. So, we will also write w equal to 0 where u is given. Yeah. So, where u is given, right. So, that means where. Okay. So, in our case, we like one example we took, we had a bar like this one and then we have B naught like this. Here u 0 equal to 0, that tells that this will be W 0 will also equal to 0. Yeah, so that's the meaning. Where u is given, where u is prescribed, then our weight is equal to 0, because we don't want to count that, because our we have to give u such a way to begin with which is going to actually accept this one. Yeah. So this is the how this is what the weak form is, and this is the condition. We apply a condition, this should be valid for any w x, however w is equal to 0 where u is given. So, or we can write w equal to 0 at essential boundary condition. Okay. Okay. So, this is the weak form. Let us simplify this further, okay, and see what happens. Okay. Okay. So, our weak form is started with weak formulation, okay, and we have 0 to L, then W x, then we have d over dx, then we have E A du over dx, right, plus B dx equal to 0, or here we are going to expand it. So, 0 to L W x d over dx E A du over dx plus equal to 0. Okay. Or so we have two terms here, one term is this one, the other term is this one. So, here we do not have to do anything. So, whatever is b x is we multiply by the, okay. So, here we can write for all w, and then we can also in this particular case w u in is given, right. So, boundary condition is given, and there we can have, so you can write we can customize this to our this equation as well later on. So, right now let me just make a general purpose, or we can write w equal to 0 where u is given, also write here. Okay. Now, this term we will not do anything. Okay. So, just write a plus b equal to 0. So, a plus this is b equal to 0, or we can find out a further. So, what we are going to do is we will apply integration of parts. So, what is integration of parts? So, integration by parts. Okay. How it happens? So, if you have, let us say, d over dx, u not okay, you have u and w, right. So, let us not write w here. So, p and q, let us say, yes. So, p times q is equal to, we have q times d p over dx plus p times dq over dx, right. Okay. So, or simply we have dpq is equal to q dp plus p dq, yeah, and hence we can write in this form integral of p dq is equal to integral of dpq minus q integral of q dp, yeah. So, this is how we can do. So, we can assume this to be p and this is equal to q, yeah. So, this let us assume it to be p and this assumed to be q. So, then integral will be equal to integral of dpq means simply pq, just pq will come out, right. So, integral of pq minus q minus this, then dp, right. So, this is how it is. Okay. So, we will use that. Okay. Okay. So, where a equal to, okay. Okay. So, again now I realize we had used a for different thing. So, we have a here already, a here. So, let us call it a1 and b1. So, let us call it a1 and b1, yeah. Okay. So, we will write a1 equal to 0 to L wx d over dx ea du over dx, okay, and then we have dx, okay, is equal to integration by parts 0 to L, yeah. So, is equal to simply 0 to L wx d ea du over dx, right, is what it is equal to, now this is p, this is q as we did earlier. So, this is p, this is q, okay. So, we get equal to 0 to L and we have d wx multiplied by ea du over dx, okay, minus 0 to L, yeah, and then we will have d q times, so we have ea du over dx, this is q times dp, so times d wx, yeah, and we can, this is wx, so we can also write equal to okay. So, next step equal to, so we get simply wx ea du over dx, and here we will have L 0 simply minus 0 to L, and here we can have equal to dx multiplied by dx, right. So, by divided by dx multiplied by dx, and hence we can have simply ea du over dx multiplied by dw over dx, yeah. or we can write here equal to here you can see here that we can write like this one WL, and then we have EA du over dx, right. So, EA du over dx, so we can write like this EA du over dx, right. X equal to L minus W0 and EA du over dx, x equal to 0 minus 0 to L, and what do we have? EA, we can write like this also dw over dx, EA du over dx, yeah. Okay, so we have our A1 is like this one, we have the B1 which is like this one, so we add them together and that should be equal to 0. Okay, so this so far we got A1. So, we write A1 plus B1 equal to 0, and hence we have WL times EA du over dx, x equal to L minus W0 EA du over dx, x equal to 0 minus after that is minus or plus. So, we have minus only. So, this minus, okay, so minus 0 to L dw over dx EA du over dx plus 0 to L Wx Bx dx equal to 0. So, this whole thing is known as the weak form. Okay, so, this is a weak form, means it is the same original equation, but this is now, this can admit more solutions than the original one. Why? Because the requirement is now different. You will not see any double differentiation anymore. So, we have single differential, single, everywhere we have single differentials. Now, this can admit u equal to alpha x plus beta. Okay. This weak form of the original differential equation or the strong form can admit ux equal to alpha x plus beta, yeah, as an approximate solution, and that is why we did this transformation. Okay. So, again here also we do not forget to write that this is true for all w, it is very important. Okay. That is this is true for all w, and w equal to 0 where u is given, right, or u is, for example, u0 equal to 0 is given, there w will be equal to 0. Okay. So, this is what the weak formulation is. Now, let us try to solve a problem with approximate solution. Okay, so we will use this weak formulation, and we will use the same example that we solved earlier. So our example is this. So this is the bar, and this is body force, which is B naught, and we do not have any force here at the end, no force here. This is fixed, so we have u 0 equal to 0, and then E naught is given, A naught is given, all constant. So equation, the original equation is E naught A naught d square u over dx square plus B naught is equal to 0. So our, if you look at the weak formulation, we will start from the weak formulations. Yeah. So our assumption is u is equal to alpha x plus beta, this approximate solution. This also you call it a test function. Yeah, you can say test function. This is test function, and wx is the called weight function. Okay. Okay. So we can, if u is like this one, alpha x plus beta, we can have wx of the same form, but different constant it can have. Okay. So let us call it cx plus d. Okay. Is the wx. Okay. And where, since wx is arbitrary, remember, so our this solution is valid for all w, that is what it says, with some minor condition that w has to be 0 where u is given. So otherwise u is general, this is for all w. So we have, although we are assuming the form of w to be cx plus d, but it is c and d could be any, regardless of what c and d you take, this solution has to be valid, and that is going to be the our approximate solution. Okay. If that is the case, then we can put these values, this and this, to our equation. Okay. So put one more condition, you see, like w0 equal to 0 we have. So that really means w, this is given, right, the w0 equal to 0 is given. So our value here will be w x, w0 equal to 0. So what we have to put is w0 equal to 0. Okay. We do not know the value of that, but only we know w0 equal to 0. Why? Because u is given at x equal to 0. Okay. So say because u 0 equal to 0. Otherwise, we do not have any condition over w. So w is equal to wx c plus d, but w0 equal to 0 because u is given at x equal to 0. Yeah. So because of that we take. Now these conditions, this test function and this weight function, both we are going to put in the weak formulation. Okay. So put value, put ux and wx in the weak form. Okay. And then what do we get? We get here, see, WL. Okay, we also have condition here, weak form. One boundary condition we also have, and which boundary condition? We also have if L equal to 0, yeah, and then because there is no force here, right? So, okay, so that means EA. Okay. So that means E naught A naught, and then du over dx at x equal to L equal to 0. Yeah. this is also given to us. Yeah, so we can identify in this weak formulation here. What you see is WL, we do not know what that is, but we can put in terms of, since the W is equal to Cx plus D, so WL will be Cl plus D, right, that is how it will be. Now EA is nothing now E naught or A naught only, and du over dx, x equal to L, but this one is force, right. EA times du over dx is force, and force at x equal to L is 0, we know that, right. So we know this one, EA naught du over dx x equal to L equal to 0. So this is general solution here, general condition here. We are now customize it to our problem, this problem now, and we find out that for our problem this term will be equal to 0. Now W0, in second term W0. Now W0, we know that W0 equal to 0 because u 0 equal to u at x equal to 0 is 0. Hence this term is also 0. So we this 0, this term 0, so both terms becomes 0. What we have now is just this and this, that is it. Yeah. So for us, simply in this case what we get is simply like this, 0 to L dw dx E naught A naught du over dx equal to 0 to L B naught, and then you have Wx dx, that is what it is, right. So you have here Wx multiply Bx is B naught only, so you have constant term here, and we have this term, and since minus here equal to 0, so this term equal to these terms. Yeah, so that is why you have like this one, where we know that u equal to alpha x plus beta and Wx equal to Cx plus D. We can write or 0 to L dw over dx. So we have simply C here, then E naught A naught, and then second we have du over dx. So du over dx is nothing but alpha, just alpha, right. Du over u is this, so du over dx is alpha, so we write alpha. So we have alpha, yeah, and then we have dx is equal to 0 to L, and we have Wx nothing but C x plus D times B naught dx. This is our what the equation is, or simply we get equal to C. C is constant, right. C is constant, E naught constant, A naught constant, alpha constant. So simply we get equal to C E naught A naught alpha L is equal to, here in this case we will get equal to B naught is constant, goes outside, and then we have C x square over 2 plus dx, and then we have L 0. Right? So after integrating this, what you get? Okay. So or C E naught A naught alpha L is equal to B naught times C L square over 2 plus D L, right. This is what you get. Okay. Or we can say we can take everything one side, or we can say we can have the C, and then we have like this one C, and then E naught A naught alpha L minus B naught L square over 2 right, that is what you have. So, with C the common we have E naught A naught alpha L minus B naught L square over 2 and then we will have plus D term and we have minus B naught L, right. So, B naught L which is the coefficient D here and this equal to 0, okay, or we have okay, we can write in the matrix form. So, we have C D and then multiplied by, okay. So, this multiplied by this equal to 0, yeah. So, we will have E naught A naught L alpha minus B naught L square over 2 and then here you have minus B naught L, yeah, and that is equal to 0. Okay. Now, the thing is C and D is arbitrary, regardless of what the value of C and D you choose, our equation is valid, this equation is valid, right. So, this equation is valid for any W, for all W with all this, yeah. So, what equation what you got here is basically we have to get rid of this, yeah. So, that then what will we get if that is the case, if this is regardless of what you are choosing, if that is the case you are getting, then our equation becomes, if you take from the first equation, in that case this one has to be equal to 0, yeah. So, okay, we have C here, okay. So, that really means we have since C and D are arbitrary, that really tells you if C and D can take any value, then this whole terms has to be equal to 0, this whole terms has to be equal to 0. Okay. So, now this term we are not saying anything so far, but we have alpha here. So, we can find out the value of alpha from here. So, let us see here. So, we have that really tells you that okay. So, we have E naught A naught L alpha, E naught A naught L alpha minus B naught L square over 2 minus B naught L square over 2, okay. And then we have the next one minus B naught times L minus B naught times L is equal to 0, yeah, okay. And this from here what we find out is equal to the alpha is equal to, from first equation we will find out that E1 A naught L alpha minus B naught L square over 2 equal to 0, or simply alpha equal to B naught L square over 2 and divided by E is that E naught, should be E naught, okay. So, this is E naught, okay. Whatever E naught, A naught L, which will be equal to B naught alpha will be equal to B naught over 2 then L over E naught A naught. So, this is what, so our x, what about beta? Beta term we are not getting, or we are getting something like minus B naught L equal to 0. So, this is the problem. Okay. So, what we forgot? What happened? Well, hence remember, because of this situation, we need to implement the boundary condition in the beginning itself. Okay. So, this one, this condition which tells you that this is equal to 0, this one we needed to apply boundary condition, or which essential boundary condition in the beginning itself. Meaning that when we proposed the alpha, the ux equal to alpha x plus beta, first thing you should do is apply boundary condition, apply essential boundary condition, boundary condition. That means u0 equal to 0, and that means we have to take alpha times 0 plus beta equal to 0, and hence beta equal to 0. So, we have beta equal to 0 to begin with, and then we are going to put the, that means ux you have to take as alpha x, and hence wx will be like cx only, and then we do all the analysis. Yeah. So, then if you do analysis, put like this one, then what you will get simply is d term will not be there. So, this equation you will have alpha here, and there is no d will be d will be 0. So, in this case cx only, that means d equal to 0. So, you have d equal to 0 to begin with. So, if you look at this equation, automatically you have this d coming to be 0. Yeah. So, this d is 0 basically. Since d is 0, hence 0 multiplied by this will be equal to 0. Yeah, and then c multiplied by this will be 0. So, what you will, in that case you will have this term will not be equal to 0. This term, because your d, because you are multiplying c times d, and d is 0 itself. So, 0 times this will is 0. If c and d you are removing, then the term here will not be 0. Yeah. So, that really means, meaning that if you have instead of having two terms, if you had only one term like ux equal to alpha x, wx equal to cx, you will get the only one term, this equal to 0, and you can solve it like that. Like we can do it right now. You put in these equations, you put d equal to 0. So, we have d0, so everywhere d0. So, this term is gone, right? This term is gone. So, you have only this equation, yeah, c times this equal to 0, and since c is arbitrary, you have this is equal to 0, and hence since you have just this equal to 0, you have alpha equal to this divided by E naught A naught L, or alpha equal to simply this, whatever the value we get, you would get just this only, there is nothing else. Yeah. Okay. So, this was the idea. So, if you had taken just these ones, you will get c times whatever the value you get here, only you get this value. Yeah. So, let us write, this is equation number a star. Yeah. So, say from a star. Yeah. So, from that equation, if you put d equal to 0 right there, from this equation d equal to 0, what we get is this one only. So, we write C times E naught A naught alpha L C times E naught A naught alpha L minus minus B naught L square over 2, B naught L square over 2, B naught L square over 2 is equal to 0. Yeah. So, when d equal to 0, we have only one equation like this one, there is no d term coming, so because d is 0, so all becomes 0, or we can write or alpha equal to my plus B naught L over 2 E naught A naught, or simply solution will be equal to, that tells you that u x equal to simply B naught L over 2 E naught A naught x. So, this is the approximate solution you got. Now, you can also plot it. Yeah. So, your exact solution was like this. So, you have x and you have u, the exact solution went like this. So, here you have L x equal to 0 here. What is the value here? So, from here to here we can write the value as well. So, our value was, you can go back, you can see in the solution, if x equal to L, then what is the value? Yeah. So, we had in very first one. So, this is the equation. Yeah. And if you put L, then what you get? You put L here, x equal to L. So, B naught L square over E naught L here. So, minus B naught L square over 2. So, what you get is plus B naught L square, right. So, plus B naught L square over 2 E naught A1, that is what you get, right. So, plus B naught L square over 2 E naught A naught. So, let us see. Okay. So, we will write here B naught L square over 2 E naught A naught is, this is the exact one, this is the exact solution. Okay. Okay. So, this is the exact solution one, this one, this is the exact solution. Okay. Now, the solution we got, it tells you u x equal to B naught L over 2 E naught A naught, and this is a linear. The final value, if you put x equal to L, so then L becomes B naught L square over 2 E naught A naught. So, actually the at u equal to, if at x equal to L, you get the same u as the original one. So, we get the solution, the approximate solution is like this. Okay, this is approximate solution. Means the end point, it has the same value in the both the cases, approximate solution and this also, this only, this is a linear, yeah, and the exact solution is the quadratic. Yeah. So, this is the only difference. Okay. So, this is how you solve with the approximate solution, and this method whatever we have learned today is called the Galerkin method. Okay, so this is Galerkin method. Yeah. Okay, so that is all for today. Okay, so in next one, in next lecture video, we will look at different method, different from the Galerkin method, or different problem. Okay, so instead of one elasticity, we may learn about say heat transfer. Okay, so okay.